Hello, everyone. Welcome to this talk, and thank you again for inviting me to this workshop. Unfortunately, this year I can't be in person at IROS, but I hope I will see you again at some other conference, maybe at Coral, where I'm going to go. Anyway, so today for this particular workshop that focuses on deformable objects, I wanted to talk about the potential of having a differentiable simulator for deformable object manipulation. And this is really work by the three researchers here, my postdoc Rika Antonova, my student Jing Yoon, and collaborator Krishnamurti. Okay, so you may wonder, why do we even care about differentiability of a simulator? And so consider for now this problem of optimizing this particular function, this objective function, for example, with respect to some parameter x. So if this function is fully differentiable, we can use powerful gradient-based optimization techniques to find local optima. And so parts of this function, they may have analytical gradients, and this can come from algorithms, like, for example, estimation algorithms, like, for example, using Real2sim in the spectrograph, or this can be a renderer to go from 3D scenes to an RGB image or a point cloud, or this can be a dynamics model, for example, is implemented in a simulator. So having full differentiability lets us basically invert the underlying process or this function and relate changes in the output of this function to changes in the input. And this differentiable component adds structural priors to the optimization problem, and you can see it as serving really as a regularizer on the optimization process. It can also decrease computation time and lead to better convergence, to better local minima. So that's at least a promise of differentiable simulation. So for robotics, differentiable simulators of the physical world are particularly promising because we can basically use these gradient-based optimization tools of any loss function. So this can be a loss function that is based on the comparison of simulator output and reality, or it can be any reward function or any cost function that we can optimize with respect to, for example, any kind of policy parameters. So here's one example from this work from Michael Luther. Or we can optimize this loss function even with respect to geometry parameters, like, for example, done in this work called diffhand. And we can also potentially optimize this loss function with respect to any physics parameters. So here is this work called diffcloud that Priya Sundaresan is going to present here at IROS in the Wednesday session, Wednesday B3. So feel free to pass by and ask her any question. So this is basically work where we compare simulated point cloud to the real point cloud and to then back out better physical parameters of actual clothes. So all of this can be done if you have a reasonable and easy to find initialization. So that's really great, and that would be wonderful. However, the reality doesn't look so rosy, unfortunately. There are fundamental challenges, for example, for stiff contact dynamics, or really in the case especially for rigid objects that have been thoroughly analyzed in, for example, these two papers. So these two papers specifically look at rigid-to-rigid contacts with nonlinearities, non-smoothness, and discontinuities. They have great analysis of the problem and the effect of gradient estimators as well. So these are really worth looking at. But they also show that, okay, there are these fundamental challenges for modeling contact in simulation and making that actually differentiable. So now the question is, what if we don't try to differentiate through rigid-to-rigid contact? Deformables may better match this idea of differentiable simulation because they are inherently compliant, and deformables should not suffer from the problem of this rigid-to-rigid contact effects and provide easier optimization landscapes. And so that's why maybe there are all these simulators, actually many of them out there, that are differentiable simulators for deformable objects. Today, basically, I will present work where we set out to answer this question of for deformable objects, differentiable simulators maybe make more sense and present less challenges. So for answering this question, we consider a variety of optimization problems, including policy optimization in tasks with highly deformable objects and liquids. We also consider Real2sim tasks where the goal is to optimize simulation parameters to make the behavior of simulated objects match reality better. So again, this is the same problem that Priya Sundaresan is going to present on in her work that will be presented in that Wednesday session. So feel free to go there as well. But for now, here the contributions of this particular work that will not be presented at IROS but at COAL is as follows. We present first of all differentiable simulation environments with various objects and interactions. We also provide a tool for the analysis of optimization landscapes and gradients. And we present also or provide a global search method for optimizing on these rugged landscapes that we unfortunately get also with deformable objects. So first of all, we construct several new scenarios with rigid objects, a particle-based simulation with fluid, and mesh-based simulation with highly deformable objects that you actually see here. And we also incorporate a number of particle-based environments from the Plasticine lab that simulates plastic deformation, as you see here on the right. So let us consider this example scenario of scooping a sugar cube out of liquid. And so what we optimize here for this scenario is the forward, back, and up, down velocity of the spoon. And we let it change, we let these values change basically 5 times per episode, yielding a 10-dimensional optimization problem. We challenged here the assumption that differentiable simulators provide easy optimization landscapes in sufficiently interesting scenarios. So our visualization of these last landscapes uncover numerous local optima, for example, this landscape for the fluid scenario. We optimize 3D velocities of anchors or pins in this particular scenario, so these are shown here in white, and allowing them to change 5 times per episode. And for this environment, this is a 15-dimensional optimization problem. And so here's again like an example landscape with flat plateaus showing the need for extending gradient-based methods with global search. Okay, so this brings us to the next this main contribution here, where we propose an approach for global search on these rugged optimization landscapes that I just showed you. So let's walk through it. So basically for the global search, this approach uses Bayesian optimization to explore the loss landscape globally. And it models uncertainty over the loss here using a Gaussian process, and reduces uncertainty globally by exploring unseen regions. So at each global iteration, Bayesian optimization proposes the next vector of simulation or control parameters, depending on the scenario, to try. So these are these red dots here. And we treat this as a starting point for what we call semi-local leaps. So we first sample a population of K candidates, and then from the best candidates, we compute the starting point for gradient descent. So this is basically using covariance matrix adaptation evolution strategy, so CMA-ES, in this local area. Okay. So the gradient descent is the leap part of the method, since for smooth landscape, it can make fast progress towards an optimum. When gradient descent reaches a local optimum, we again sample K candidates in a gradient-free way, as described before, from a Gaussian distribution whose mean and covariance are computed using this CMA-ES equations, essentially. So we again compute the descent start from the updated mean that is obtained from the best candidates, and then run another gradient descent, and so on and so forth. In the outer loop, we update the Gaussian process posterior for Bayesian optimization. Then Bayesian optimization selects the next point to try globally. So again, it tries to find these red points here, and ensures to return to low loss regions to further improve within the promising areas of the search space. So in the experiments, we first show that gradient-based methods can offer significant gains compared to gradient-free approaches, such as CMA-ES. And here's an example with a 3-link pendulum that has to reach the blue dot. So let me just replay this, how the solution actually looks like. Next, we study a variety of scenarios that use particle-based simulation, starting with this fluid scenario. And where our method, here shown in black, outperforms other gradient-based algorithms in lifting the cube out of the liquid. And so we actually observe even larger gains for BO-LEAP in this rope scenario, where it succeeds to wrap the rope fully around the pole, while CMA-ES still leaves a gap. And BO-LEAP also has strong performance in the scenario with spreading the dough evenly across the board. So the light blue gaps here show up in the case of CMA-ES, while BO-LEAPs makes a more even spread and really aligns with the desired goal shape. So we also did some experiments for this Real2sim transfer. So this is our experimental setup with the real robot that consists of a Kinova Gen 3 robot arm, 2 RealSense depth cameras, and a deformable object. The objective is to optimize simulated cloth motion to match reality. So this is also the scenario, by the way, that DiffCloud explores, which you can talk with Priya Sundaresan about at this Wednesday session, just mentioning this again. And so here's this optimization landscape again for this particular scenario when lifting a rather stiff piece of paper. So while some of the dimension of the loss landscapes here are actually smooth, others are pretty rough, making this gradient-based optimization hard. Nonetheless, gradient-based methods actually perform quite well. So here's an example with optimizing the simulated deformable to behave like a paper towel when lifted. Here's an example with learning to match the behavior of a highly deformable cloth. BO-LEAP further improves over other gradient-based methods in this scenario. Although differentiable simulators can be paired with BO-LEAP to make fast progress on rugged landscapes, there are still some limitations we need to highlight here. And the biggest challenges of optimization with differentiable simulators arise due to difficulties differentiating through rigid contacts. Maybe as expected, right? So with this pinball, we let users study this issue by varying the number of colliders and thus changing the mean number of rigid contacts per scene. And so here, again, you have this visualization for for quite a few colliders. While here's an example with fewer contacts, and you see this optimization landscape changing accordingly. Here's another example, this time contacts between a rigid and a highly deformable object, this pancake, yield a very rough landscape and low quality gradients actually. And this is despite the fact that the dynamics of the environment as visualized on the left actually appear fairly well behaved. So to summarize, here's the message that we would like to communicate with our work. The first takeaway is that well-behaved dynamics does not necessarily yield smooth loss landscapes and useful gradients for maybe using gradient-based optimization. The second takeaway is that particle-based simulations often yield high-quality gradients, So they could be useful despite the increase in compute and memory requirements compared to other simulators. And lastly, global search with semi-local leaves can be a valuable tool to tackle rough optimization landscapes. It is beneficial for optimizing the more advanced differentiable simulation scenarios that have various kinds of interactions and deformable objects. So if you want to find out more detail about this particular work, then I invite you to check out the paper that is online or scan this code. This work has really been done by Rika, Jin-Young, and Krishna. And I thank you so much for your attention. I'm sorry that I cannot be here live and answer questions, but maybe I'm able to asynchronously answer them. So thank you very much for your attention.